The Alternative Natural Philosophy Association presents Clive Kilmister, Ted Bastin and David McGoveran in conversation during the month of December 1992. The recording took place in Cambridge.
The problem arises with the definition of dimension. Now, there is a division here because I think that the dimensional structure of space corresponds with the three levels of the hierarchy, just to put it in a very crude form, and that this is apparently a facile and perhaps retrograde step, I mean a silly step, but one has to divest oneself of all the classical ways of thinking and think, well, what do we mean by dimension? And of course we've spent, Clive and I anyway, have always been pressing at this question, and we've got partial answers and answers in terms of symmetry and so on. The one thing that emerges is that if you're taking a combinatorial, as we used to call it one time, an algebraic point of view, there isn't an answer coming from conventional theory. It's just a thing which is glossed over. You know what dimensions are in, shall we say, statistics, and you can have spaces of different dimensionality, and it's assumed that the same mathematics applies to physical space, and that the dimension number is just a fact of nature. Of course it's three-dimensional, that way, and that way. And this was not adequate for us ages ago, and we did actually go some way towards solving this problem in terms of the nature of symmetry, and it was to solve that problem that we first got notions of what's since called indeterminacy. I mean, what am I trying to say?
Similarity of position and
well, the similarity of position as we developed the notion then. That's actually a more sophisticated notion but then Parker Rhodes came to develop his whole picture from. But it is related. I mean, the germ of it is in there. And now we see it still coming up in the context of ergodicity, the requirement to treat things indifferently when there's no reason you shouldn't. This is essential to the mathematics. It appeared right at that early stage, right back in the early 50s. But now we find that the problem is still with us. We have this combinatorial structure. Where do we locate this number 3? And we have the perplexing situation that it's located in that particular number, not interpreting it for the moment, exists in the second level, the level at which the strings are of length 4, because there are 3 discriminately closed subsets, and this satisfactorily ties up with the earlier definition in terms of similarity of position. In fact, the quadratic group that we worked with there is isomorphic with the structure of that level in the hierarchy, almost accidentally, since Parker Rhodes started to develop the mapping algorithm from without having that in mind at all. So that was really a significant thing. Parker Rhodes, I think, thought that the dimensionality was quite obvious. You had a 4-1 structure, and that would be it. He didn't develop the notion of a discriminately closed hierarchy, which became essential later and made the algebra, well, simplified the algebra, and it made it, I think, to my mind, comprehensible. As when it was conceived on the analogy of wave vectors and eigenstates, it wasn't. I don't think it was comprehensible. It just did what it did as a sort of surprising thing, which we spent a long time sorting out. However, so we've got this appearance of this characteristic number 3 there, and a lot of arguments, including those of David, put great emphasis on the fact that it's in the nature of dimensions to be completely symmetric, to have complete symmetry. Now, I can't remember precisely how his arguments are developed on that score, but I know it's agreed that it's important. So why did we switch to this notion of identifying coordinates? Identifying the dimensionality of the space with the levels. Well, of course, the idea Clive mentioned the other day is part of it. If you're propelled towards a one-dimensional structure, then the first deviation from it, that is where the first time you can't fit everything into that picture, requires something new, and then you may require something new again, and then the picture fits nicely that you can't do the same. There's no way of doing the same trick yet again. Perhaps, as people are always quoting Pierre's example of what you shouldn't do, I will, for my own purposes only, say that Pierre has backed me up on this particular thing, and that Clive actually has come round to this point of view recently, and his arguments will be far more cogent and expressed with much greater mathematical exactitude than mine. So maybe he'll come on, he'll mention what made this change of heart of his in a moment. I want to push on. These dimensions are to be distinguished from coordinate structures. Here I differ from David. I think his development is very different from this. The coordinate structures exist in the mapping space, or the dual space which represents the ordering, whereas the dimension structure is essentially unordered. It derives from the unknown input. I won't call it the random input. We don't know what ordering is, and we expect that when we're dealing with more interesting things than where tables and chairs, not to speak of ghosts, can appear, and things going through walls and all that sort of thing, and the laws of physics are well and truly flouted, then that will correspond to events which significantly deviate from randomness in the background. The use of the word indifference is because it seems to us important to emphasize that the mathematics is built on depends upon the proposition that no order is preferred above any other, and that every element of a relevant set is treated mathematically in exactly the same way as another, a principle I've always thought to be mathematically of extreme power. But you're in the paradoxical situation that all the interesting detail of the world depends on that not being true, and yet you describe it on the basis that it is true. Well, that's something we have to live with. I mean, it's quite a profound situation. It's not incompatible in any way. It's just that you've got to realize it and cope with it, and recognize, I think, that it provides you with a basis for thinking of all physical laws as essentially approximating character, because you're using this background structure which can't work unless what it describes deviates from its own basis. Well, then, so we have a labeling system, as Clive would call it, which derives from any presentation of the hierarchy structure, and that has the formal aspects of a coordinate system, but that's as far as it goes. And we have to look at how we get it into something more like what the geometrician and the macroscopic physicists think of as coordinate systems. And here it seems to me that through the way our development has taken place, we must give pride of place to the phenomenon on which relativity depends, namely the limiting velocity of light. And I think it's to me obvious, but it may be disputed, that since we've calculated coupling constants and since velocity of light appears as one of the necessary factors, I mean there has to be a factor with that dimensionality in the coupling constants, the dimensionless constants, therefore we shall expect that the finiteness of the world, the finiteness of the imposed by the hierarchy picture, and in fact any kind of finiteness, any kind of finite limitation on the numbers of things that they can be, would exhibit itself in terms of a finite velocity of light. To put it round the other way, we know that there's got to be a breakdown of our description. It's not at all unreasonable, and I think is necessary. It should correspond with the breakdown of the classical description which gave rise to special relativity. Now, how much further can we go? The metrical attributes of just geometry, I mean Pythagoras' theorem, seen from a combinatorial point of view, which is now taught to school children, where they, inverted commas, prove Pythagoras' theorem by counting up the dots in a square array. Well, I mean, I think this is laudable. I think this is a sensible way to teach it, except it doesn't take it the whole way. Gives a hint to this. What we're talking about is orthogonality of sets. There's a tie-up between the way you can treat a right angles and therefore a dimensional space, with the fact that, which is right in the heart of the hierarchy picture, that if you treat sets, I don't know if I should call them sets, anyway I call them sets, according to the principle of indifference, then the mathematics you're to employ has got to treat every element exactly the same as every other. This is a very important thing in justifying, to my mind, I mean I'm a simple-minded sort of way, of justify matrix multiplication, which does exactly that. It's the most general way of preserving it, of relating two sets while preserving the indifference principle. But that applies in a special case to the Pythagoras construction seen combinatorially. Now, the next jump I make, which is outrageous in the way that mathematics always comes to me, but I think it is a serious mathematical idea, is that we should make a partition between the things that fit into the geometrical scheme, and we've only got one thing that does so far, and that's the limiting case of the velocity of light. We should make a partition between the input into those things which satisfy the orthogonality condition, and they're going to be squares, and the bits left over, this is the crudity of my thinking about this, the bits left over are unordered and simply appear, the number of them appears by itself, it's just that number, whereas the other things where you're dealing with a dimensional space correspond to the square, have to be taken as the square. And then, having come to this outrageous conclusion, I was then forced on my attention that I was really reinventing what David had already invented and what had been rather notoriously described as as adding in quadrature, which he'd already introduced in the study in the microscopic study of the hydrogen atom. So I was proposing to use that as the introduction, as a way of introducing spaces which, the full concept of a dimensional space, of a coordinate space, sorry, so as to tie it up with dimensions. And in that case, you can give some substance to the notion, which otherwise just remains a pure convention, of treating the fourth component, which you have to have in the mapping space, as time-like, because of its appearance in the relativistic limit.
It bothers me considerably this identification of concept of dimension with levels of the hierarchy, primarily because of the difference in cardinalities between the levels.
Yeah.
And that seems to give a preference to one of them. And if you have some way of making them all in the levels indifferent, then I don't know how to distinguish them anymore. So I get into trouble knowing that I've used up one dimension and have to go over to two dimensions to characterize some construction. It also bothers me that you want to separate the notion of dimensionality from things that are ordered. It seems to me that one can't know that you've used up some dimension, whatever that means, unless you have some concept of ordering. And this may be a very crude kind of ordering, it may not be a metrical kind of ordering, but it nonetheless, I think, is essential in order to know when additional dimensions are needed, that it's 1 versus 2 versus 3 or whatever. I also have trouble saying it when you say you can't go beyond 3. There's this notion of threeness seems to me to occur only in the metrical notion of dimensionality, not in, shall we say, the parametric notion of dimensionality.
What is that?
Until I can actually start talking about measurement with respect to dimensions as coordinates, and again, whether they're very carefully laid out and mathematical or not is sort of irrelevant, but some notion of ordered dimensionality and being able to put some kind of tick marks along a given dimension and so on. That until I can do that, I really have no reason to say that space is three-dimensional. If all I'm talking about is saying these are independent classifications of things, and I've used up this classification, so I have to go over to the other classification, which is sort of the what I gather you mean by dimensionality as distinct from coordinate spaces, then I see no limitation on 3. It's rather convenient to have independent classifications greater than 3 and common.
To a large extent, it is, as I see it, it is a matter of defining dimension at this stage. And if I say, well, I will define it, then, as in the way I've suggested, then that would, I suppose I've spoken in a confusing way and behaving as though I were making an identification when what I'm doing is making a definition.
Yeah, but then I have trouble with your definition, as I've said.
Oh, yes,
I think it sounds very inconsistent then. And precisely because the definition that you gave me seemed to imply some kind of ordering as being necessary.
Well, there's 2 points. There's the symmetry, and there's the ordering. I've thought a great deal about the symmetry, and it got to the point where it doesn't worry me because you've got to start somewhere.
Yeah. But I don't know how you can talk about needing additional dimensions unless there's some kind of ordering involved. And at the crudest form, it's some form of counting. But counting is ordered. It's unless it's ordinal type of counting, it doesn't really help us much. And so, to me, these things are closely tied together, and I think there's kind of a colloquial usage of dimensionality, which is very imprecise and not terribly useful. And there is a far too restrictive notion of coordinate spaces, which involve a rather simplistic Euclidean view of coordinate systems and so on, and doesn't take into account the fundamental aspects of supplying a coordinate system. When I'm convinced at this point that when you are more careful about what you mean by supplying a coordinate system, by supplying any kind of measurement scheme, that these two ideas sort of meld together. They become like a kind of a spectrum of concepts, not distinct ones. And in that sense, then I have once I'm at that point, then I have a lot of trouble going on to the next phase of your argument, invoking Pythagoras and so on and so forth. I think Pythagoras has to come out of the combinatorics rather than the other way around. This has to be of a statistical character.
That is what I was claiming.
Is it?
Okay. Saying, yeah.
All right, yeah.
I'm worried about that, but I'll come in later.
Okay. And I think that the business of the speed of light as a bounded set of values is a natural consequence in any finite system, that you're going to have something that will behave this way.
Yeah, you agree with me on that.
Yeah,
broadly.
yeah. But I don't think that's that per se is the crux of any metric character of the space. It may be one way of getting at it, I suppose. One way to start the whole thing off. I guess.
Okay.
Comments to date.
Well, let me try and answer for Ted about the question of the three levels of the hierarchy, because this was the sticking point for me for a long while, but I've gradually managed to convince myself that it's not the sticking point that it was. And I suppose when you've gone through a process like that, it's very hard then to remember why it was such a sticking point. I think that it's partly a question of one's way of thinking. If you start, as I naturally did, from the position of a mathematician who'd been taught all about vector spaces of dimension n and so on, and then look and say, and in the real world, in our ordinary perception of events, n equals 3. How curious. Now this is a beginning from which it is then very difficult to tackle the problem of dimensionality in the real world. Mm-hmm. Instead, one should start by forgetting all about vector spaces and so on, and say, as with Kant, for example, all our experience takes place in space and has a certain threefold structure about it. Now, well, that's half of Kant. I mean, space and time, he says, and the time is separate. So let's leave the time out. The experience has this threefold structure, and if you stay at that point and don't try and put any more on the definition than that, don't try and embroider it anymore, you could at once say, oh, how strange, because here we have the hierarchy and everything has a threefold structure. So isn't that a candidate for identifying these two threefold structures? Then if someone says, well, but the three levels in the hierarchy have different degrees of complexity, I'd say, well, that's a bit like our finding out about our experience in the world following Kant. That is, the amount which one is able to digest, imagining that everything's in a straight line, is relatively small. And one rather quickly gets to the situation where some other apparatus is needed to rationalise one's experience, and even that one doesn't carry you much further until you've got the other one up here. So the I mean, I'm putting it very crudely, but this seems to me to show that the different degrees of complexity of the hierarchy aren't an absolute barrier to understanding the three levels as being the cumulative threeness of experience which comes out of beginning at a rather primitive level and gradually getting more experience.
Well, perhaps this is a transatlantic thing, but my perception of what I can organize and understand in one dimension is not so vastly different from what I can understand in two dimensions as the degrees of complexity differ in the levels of the hierarchy. And these seem to be extremely different in character. And they certainly are not symmetric. I can't flip them about.
No.
My world of experience doesn't seem to care which way I orient.
It is a problem about people who have had, I was going to say, an excessive mathematical training, but really almost any mathematical training, which has then managed to shut themselves to this obvious characteristic of experience. I mean, obvious once you've got yourself into my state of mind, and shut it off by all this business about symmetry. You know, you've got in your mind uppermost the orthogonal group. Oh, sure, it turns coordinate systems round. This is a terribly latent derived thing, is the argument we are trying to put to you. You know, you may not accept it, but it...
No, I don't accept it, because from a very early age, my experience of the world was not only physically and three-dimensionally visual, but more than three-dimensional. And I to this day, solve many problems by visualizing them in my head, as it were, in more than three dimensions. And that comes as a gestalt. It does not come as a, in fact, to a large degree, my interest in mathematics was driven from this experience, not the other way around.
Well,
so it's not. I don't think it's right to say that one gets convinced of this kind of three-dimensional view of the world and its symmetry and so on and so forth from mathematics. I think that the notion of multidimensionality, once the notion of independent properties of any kind, however you wish to define that and understand that, bits and pieces that I can't explain with one concept. Once that's understood by anyone, and I think that's essential to understanding the notion of dimensionality at all, to even use the word, then I don't think that there are very many people who will perceive the world as unidimensional or heavily unidimensional and diverging from it only because they are forced to.
Perhaps you could explain to me, as a reader who found it very difficult to see that you weren't just feeding in ordinary physical space into that picture. Well, I mean, you seem to have regard the coordinate system as a structure which is obvious, or in the connection between dimensionality and coordinates.
Well, yes,
where
this is
does
something.
the three come from for you?
Yeah, I think this is something that you have often quoted me as saying, and I've never understood. You frequently said that this coordinate system business is built into my approach early on, and I don't see that as being true at all.
Where does it come in?
Very late on, actually. It's extremely difficult to get to it. It requires a tremendous amount of structure, of shall we say, combinatoric variety, before one can start to talk about anything that even remotely resembles coordinate spaces. And try to...
So to cut a long story short, or rather to ask you to jump straight in at an advanced point, where does the number three come from?
Okay. When this so-called to refer to what Pierre likes to call McGovern's theorem again.
You do it with the Feller result.
Yes, Feller's
Yes,
argument.
quite. Yes.
But that is based upon that's why it becomes 3 plus 1. But the definition of dimension, the understanding of dimension in this kind of construction, the understanding of coordinates and so on, is built up from very simple conceptual requirements. One of them being, for dimensionality, it's the notion of independence. And this is context sensitive. You can't talk about two things being independent except in the context of that construction. Things may become coupled if you change the construction. Right? It's only a matter of how much information we have. So in some sense, the notion of dimensionality is artificial in that sense. With coordinate spaces, this is a matter of identifying, locating, however you wish to describe it, similar patterns in the combinatoric plenum. And once that is done, remember that in the ordering operator calculus, all of this combinatoric variety, these various events, are highly ordered. They are generated as a process of ordering. There's the notion of unorder, of lack of order, exists only in the sense that one says, I have all possible orderings. Okay? I have too much order, as it were. I can't differentiate anything. So I don't have unordered events. I have overly ordered events only. And otherwise the things are unconnected. There is literally no connection, whether they belong in different spaces, constructions. You can't pull them together.
But you do characterize the quantum situation as being one in which is essentially unordered.
No, not at all. No. Unordered in space and time, yes, perhaps, but not unordered. Never.
Unordered in space and time, I see.
Yeah.
Yes, all right.
Yeah, the space and time kind of ordering comes out, is superimposed, as it were, but arises out of an insistence on the identification of instances of the quantum number, say, or a mass property or some other thing, saying that these two things are identical. And then that's sufficient to force a spatiotemporal structure, actually a causal relationship. So at that point. But no, lack of order doesn't exist in this particular view. So the metric structure comes about through specifying ordered sequences of like patterns or constructs, portions of the overall construct.
And then you appeal to this rather special Feller result.
Right. The Feller result only deals with probabilities of one being able to specify such patterns in a uniform way in where there's a multiplicity of their generation that is independent, mutually independent. And the Feller result says that statistically this will become not impossible, but almost impossible to do in more than 3 dimensions.
Yes.
So, 3 independent ways.
Because this arrived on the scene comparatively late. I mean, we've been studying ordering operator calculus for a long time before that.
It was in '86,
Yes.
so 85 or 86. Yes.
So, and this, we,
Right.
from our point of view, or from my point of view anyway, this question of the nature of the three-dimensionality was something that needed to be answered
Right.
pretty early on, and it's partly the historical development which has made it difficult to fit in.
Yeah, yeah. I think it arrived prior to the publication of Foundations of Discrete Physics, or if you can call the SLAC publication, or even prior to that, prior to my draft of it. So it arrived certainly along with, let's see, I guess what you might call the second version of any paper that I produced on the ordering operator calculus for consumption by this group. And the part of this has to do with the approach of the ordering operator calculus, because I was trying to set things up in a logical presentation, not necessarily that is one to set up an axiomatic type structure in the presentation, not one that was driven from experimental or experiential considerations per se. And so that's the order of presentation in the paper. As a result, concern about whether or not space was three-dimensional or 16-dimensional or 10 to the 38th dimensional was never even considered until about the 84-85 time frame.
Mm.
You're concerned, I think, in the ordering operator calculus, as we are, with a discrete space.
Mm-hmm.
And there's a good sense in which, in a discrete space, if you have suppose you've got enough structure, you've actually got a coordinate system now. That is, you label points with 3 rational numbers, or even 3 integers.
Okay.
Such a labelling is logically equivalent to labelling them with 1 integer.
Mm-hmm.
The three-dimensionality collapses, rather, if you perform a transformation like
Mm-hmm.
that.
Mm-hmm.
If you have unlike any of us, you are one of these unregenerate people who has a real number field up his sleeve, and he has 3 real numbers labelling the things, and then he has a 3-dimensional structure. Well, so the example is usually given in 2 dimensions. He has 2 dimensions, and he has a mapping on the 1 dimension, say by one of Cantor's space-filling curves.
Mm-hmm.
You can at once cut him down to size by saying, no, that's no good, not bicontinuous. But in the rational case, there's no such way of shooting him down. And if you say you've got a 3-dimensional rational space, he can come along and say, oh no, I do this and this and this. There, you see, it's 1-dimensional.
Mm-hmm.
Or, of course, he could go the other way and say it's 4-dimensional.
Mm-hmm.
So it seemed to me that in the rational space which you're concerned with, which we're concerned with, this notion of 3-dimensionality falls to the ground unless it's propped up with something else. And what we prop it up with is to go back to experience and say, no, this, you see, with the help of the rationals or transformation of the rationals or whatever, is not going to alter the fact there are 3 levels of the hierarchy.
Mm.
And so there's the threefold character of experience, just like old Kant said.
Yeah.
Did he? Did he discuss dimensionality?
Yes.
Did he
yes.
really? Oh, I've forgotten that. I haven't read it since I was
No.
at school. But
Well, it is one of the... I mean, I'd have to go and have another look, because I tend to read more into him than he really
Yes.
says. But it is there, yes.
Yeah. There's, I don't, well, I have a problem with that particular argument because it is, it does violence to the notion of dimensionality. One of the reasons why the...
well, I would say to the notion of coordinate.
No,
Dimensionality.
I mean dimensionality.
The number of independent ways you need to describe things.
Right, yes. Because one of the things that I found attractive, what led me to reinterpret and modify somewhat Feller's theorem, was that I felt one should not be looking for whether or not things can be collapsed, but can they be expanded? It is not a question of why can I not view the world in 2 dimensions? Of course we can view the world in 2 dimensions. You know, we can see things on a
does
television.
it all the time,
yes,
yes.
right, exactly. So of course we can do this. But the notion of projections is an old story, and I, regardless of whether one lives in a real number field or an integral number field, a discrete space, I can still do this projection business. Now, but the issue as to whether or not I can uniformly divide the space in such a way so that there are independent, mutually independent and equivalent, you know, to some degree of equivalence, some form of equivalence, subspaces, is quite another story. And what Feller's theorem says is that you simply can't do it. Well, it's not that you simply can't do it. It would have to be an extremely special case, a highly artificial case, which you would have to, there would be a few algorithms for generating the space that in fact what they do is they turn out to be equivalent to having an embedding in a continuum background, so that you know a priori what this kind of metric condition is.
Well, I'm sure Feller's theorem comes in.
Yeah, but my point is that I don't think that the argument about collapsing this notion of which is equivalent, I think, in a real space to projections is a good argument.
No, it's not equivalent to projections, because in projections you lose information. But in these things you don't lose any.
Yeah, I'm not sure that's true. Yeah, I'm willing to. That would have to do with, gosh, well.
Well, I mean,
I think let's restrict ourselves to the discrete case. In a discrete space,
right.
We don't have to worry about whether or not the compactness of the number field and all that. And
oh no, I wasn't going to be so clever as that. I just meant you lose information. I mean, sure, if you look at the television picture, in some way which I don't fully understand, you don't seem to have lost very much information. You see there something which the eye takes as equivalent to the virtual reality, as it were. Sure. I mean, it's done by sort of shading and size and all sorts of complexity.
Magician's tricks.
Yes. But if you think, suppose we have a 3-dimensional situation, we make a plan of this room. So we make a 2-dimensional projection. And so you get bits of the projection corresponding to that whiteboard, but you don't get how high it is. So you've lost information when you make a projection. Whereas the kind of transformations I was talking about with rational numbers, nothing is lost. You can take it to bits again and get back to where you were.
Yeah. I don't think that's absolutely essential to I was using projection in a less, probably a less strict sense than you were. I was treating it almost as, shall we say, squashing the thing down, and treating height information as information that you can say, well, it's physically located up here, but I can push that height information down here and keep it on. When you take a discrete space and convert the multiple orderings of each dimension into a single total ordering by going from 3 coordinates attached to each object, discrete object, to a single one, and they're all enumerated and kept distinct and so That depends on a number of things. One, it depends on the notion that you do have, in fact, a cardinal in that is large enough. You have enough labels to use a single label for each of them.
Yeah.
So you're doing the same kind of shall we say, mushing things down,
Yeah.
flattening them out, and you're relying on, in doing that, you're relying on having enough labels to go around.
Sure. Sure.
So-
I mean, I think this is a difference, probably not an important difference, but it's a difference between us, you and Pierre has copied this, have this stated cardinal that nothing's going to get bigger
Yes,
than.
yes.
This must, I suppose, come from your experience with machines.
Well, not really. It's I think certainly machines are good ways to exemplify the problem, but if I can allow n to go on forever and still talk about finite and discrete, I mean, this is the old problem of the calculus. I take limits and so on. I can do the division, and at what, where is the difference between them?
I think you're being excessively cautious in wanting to state a particular cardinal that you're not going to exceed.
Yes,
It seemed to me that once you've stated that you're dealing only with finite numbers, that's okay.
Yeah, I think that it actually has important use in the sense that I need to know when, in terms of the particular construction that I'm dealing with, I need to know when the space gets enlarged. Okay? That is,
No,
when n needs to be restated. And
meaning that
I always need
cardinal
to know
gets
what that
enlarged.
cardinal, what it changes to.
Right.
If I don't know the cap n, the maximum cardinal at any given time, I really can't talk about, in this discrete world, about things like the speed of light. I have no bound on my ranges. It's an unspecified bound.
I see.
It's arbitrary.
So the finiteness of C, for example, is coming for you from the fixed value of the cardinality, the maximum cardinality.
Yes, that's right.
I hadn't realised that.
Yes.
And I guess you probably think, though you might not want to say it publicly, that we shall find the need for some such thing in our work, which we certainly hadn't envisaged doing. We had imagined getting C with sufficient work out of the sort of things that Ted has been saying.
Yeah. No, I think it will be essential. Yeah.
I see.
Yes. I will say that publicly.
Well,
yeah.
that... okay.
I haven't quite got the point. It would be essential to have an absolute numerical upper bound of any number that you can give physical interpretation to.
No,
No.
any number that's allowed in the calculus.
It is not that. I want to try and be clear about this. It is not that I see that you must state some magical number, maximum number, up front at this stage of our understanding and so on, and then remain dedicated to it now and forever. But rather that you recognize that there is such a number and that you be willing to understand the changes that this makes to, in particular, to the topology of the discrete space when you change it. If you have to reevaluate whether or not constructions within a discrete space are distinguishable or not when you change the cardinality, because it changes the connections that are possible. It changes the variety. And so now things may become connected, may become indistinguishable in ways that they weren't before.
Oh, I see.
Right?
It's a very interesting idea, I must say.
See, it's not an absolute limit. It reminds me rather of what I used to think of as, until last week, I used to think of as the credit limits on credit cards. I mean, we have credit cards with the limit on, and if you get anywhere near it, they write to you and say, I notice you're approaching your credit limit, perhaps you'd like it raised.
That's actually a very good example, because in fact what happens is if you were to call them up, let's put the foot on the
that
other,
would be different,
or the foot in the other shoe, rather than the shoe on the other foot. If you were to call them up and say, I'd like it raised by such and such amount, there is a reasonably good chance that they would say no. And the reason for this is that based upon your buying patterns and so on and so forth, that is to say the constructions that you've created so far, this cap in is set with a plus or minus on it, something that is considered to be reasonable, that doesn't perturb the system too much, right? And you know, the situation I'm describing is quite similar.
I see.
You don't want it to be, if you perturb it too much, all the constructions that have gone before do collapse. Right? And so you need to reevaluate. I think Pierre has said this on a couple of occasions in things he's written, that whenever we change in, if we increment in by 1 even, we have to reevaluate our conclusions from before. Any computation of for him the beta, the velocity, has to be reevaluated. It is not the same thing anymore.
I see. I can see that to have this limit certainly shoots down my argument about the lack of dimensionality in a discrete space. I mean, in a way it does anyway, but it prevents, it would allow small scale mucking about with the dimensionality, as long as I didn't try and do the whole space. And
right, yes. Which is exactly what the Feller's theorem result says. It says that locally, as it were, for small subspaces of this thing, you can have many dimensions. And this parallels, to my thinking, the kind of thing that you see in quantum mechanics. That is, we can define for extremely complex, highly dimensional objects in quantum mechanics, quantum field theory, and this seems to work quite well, and you get some good predictions out of it and so on and so forth. But if you try to extend this, it all starts falling apart.